First of all, a shout out to my super manisan friend. I hope to see you all soon. Inshallah. Today, I am going to discuss with you sight distance for horizontal surface. In this lesson, we are going to explore the physics behind the distance it takes to stop a moving car. So we are going to learn the differences between lag distance or thinking distance, the braking distance, and the stopping distance. And finally, we will calculate how far it will take a vehicle to stop and how to estimate this distance based on its initial conditions. The ability of the driver to see ahead along a section of road is very important for safe and efficient operation in highway traffic. Thus, obstacles should be clearly visible to the driver some distance ahead. That distance is what we call sight distance, or the actual distance along the road surface at which a driver from a specified height above the carriageway has visibility of stationary or moving objects. Imagine a car traveling at a certain speed when an elephant suddenly crossed the street. The driver has to make a decision to stop to prevent him from an accident. The total distance a car requires to stop is called the total stopping distance. This is the sum of the distance covered in the time it takes for the driver to react, known as the lag distance, and the distance the car travels before coming to rest after the brakes are pressed, called the braking distance. Let's go into detail regarding the process of braking and stopping, starting with the moment the driver saw the elephant. The driver in our scenario decides to stop after seeing the hazard. Making the decision to stop takes time. Not a lot of time, but it does take time. The distance traveled by the vehicle while deciding to stop during the total reaction time until the brakes are applied is called lag distance. Reaction time is the time taken from the instant the object is visible to the driver to the instant the brakes are effectively applied. Using kinematics, we can now get the equation for lag distance. The velocity of the car can be thought of being constant during the short amount of time. So all we need is the speed times the reaction time to get the lag distance. Since the reaction time of a person wanting to brake is generally less than a second, this distance is the smallest relative to the braking distance. Therefore, lag distance is equal to the initial velocity of the vehicle times the total reaction time. On the other hand, braking distance is the distance traveled by the vehicle after the application of the brakes until it will stop. Deriving the equation for the braking distance is a little more involved. We start with the kinematic equation Vf squared is equals to Vi squared plus 2AD, where Vf is the final velocity, Vi is the initial velocity, A is the acceleration, and D is the distance traveled. We know that the final velocity is 0 because the car has stopped. The only unknown in this equation is the acceleration A. Because there is an unbalanced force on it, the car decelerates, or accelerating in the opposite direction of its motion. The brakes provide friction to the wheels, slowing them down, but the static friction F between the wheels and the road is ultimately what stops the car. Air resistance and rolling friction are involved, but to a lesser extent. The weight of the car mg and the normal force N are the vertical forces, and they are equal. Newton's second law of motion describes the relationship between an object's mass and the amount of force needed to accelerate it. To calculate the acceleration of the car, we are going to use Newton's second law, summation of F is equals to ma, as our equation 1. Upward and to the right being positive will be our sign convention. Friction is calculated by multiplying the coefficient of friction mu and the normal force N. The normal force is mg because it only has to counter the weight of the car. Using equation 1, we have to sum up all horizontal forces involved. Since static friction provided by the brakes to the wheels resists the motion of the car, it has to be negative. So, negative f is equals to mu n, or negative mu n is equals to ma. Mass will be eliminated. Thus, it gives us the acceleration of the car, negative mu g. Substitute a to the kinematic equation, where final velocity is equals to 0. We will obtain 0 squared is equals to vi squared plus 2 times negative mu g times d. Now we can write the equation for d as negative vi squared divided by negative 2 mu g, or simply vi squared divided by 2 mu g. Therefore, braking distance is equals to vi squared divided by 2 mu g, where vi is the initial velocity in meters per second, mu is the coefficient of friction, and g is the gravitational acceleration, which is 9.81 meters per second squared.